Well, greetings you all. This is Matt Roscoe at the University of Montana, and this is a video for our section on sequences, the start of chapter 9.1. So we sort of switch gears at this point in our study of calculus. Up to this point, we've been studying mostly integration and difficult, ways or difficult settings where we need new tools to integrate. So places where integration by parts or integration by trig substitution might be helpful. And then we moved on and talked about where integration can be used, some applications, area and volume, work, force and pressure. And so now we sort of shift gears and take a look at an area that at first glance doesn't seem like it has a lot to do with what we've been studying so far. But as we build up, we'll find out that it has quite a bit to do with integration. So off we go. So I want to define what a sequence is. I want to talk about how the different ways that we represent sequences. And then we're going to talk about convergence and divergence. And in that same vein, we'll talk about when sequences are bounded and whether or not they're monotonic. And how we can use boundedness and monotonicity to get a sense of sequences' behaviors. So off to the races. Here we go. A sequence is any infinite number list of numbers. We call S sub 1, S sub 2, S sub 3, S sub 4, dot dot dot, S sub n, dot dot dot. And we call that first term S sub 1. S sub 2 would be the second term, and S sub n would be what we called the general term for the sequence. So let's dive right in and take a look at a few sequences and think about general terms. So we have these sequences. I'll write them down here before switching over to the ElmoCam. 1, 4, 9, and 16. 3, 8, 13, and 18. And let's see the third one, 1/3, 2/5, 3/7, 4/9, and 5/11. Okay, I'll go ahead and switch over to my ElmoCam here and we'll work on these. Okay, so let's take the first one. So on the first one, what we can kind of think about is S sub 1 is equal to 1, S sub 2 is equal to 4, S sub 3 is equal to 9, S sub 4 is equal to 16. And what we're looking for is a general term, S sub n. In other words, how would we, knowing that we're in the nth position, calculate the nth term? And oftentimes what this boils down to is trying to rewrite these in terms of the subscripts over here. So, one thing I notice is that 4 is equal to 2 squared, and 9 is equal to 3 squared, and 16 is equal to 4 squared. And now I can see 1 is equal to 1 squared. So it seems like what's going on is, in general, this number, 1, 2, 3, and 4, is the same as the subscript on the sequence position. So in general, the nth term, or the rule for the sequence, is that S sub n is equal to n squared. And of course, a quick check would be, what would S sub 5 be? That would be 5 squared, which would be 25, and that does seem like it makes sense. It's the next perfect square after 16. So this sequence is just a sequence of perfect squares, and its nth term or general term is S sub n is equal to n squared. Let's take a look at another one here. Number 2, we have, let's see, S sub 1 is equal to 3, S sub 2 is equal to 8, S sub 3 is equal to 13, S sub 4 is equal to 18, and what we want to know is, how can we write S sub n? So one thing that helps in this one is I can see that they're all equidistant, right? taking a look at each one of these, I can see I'm just adding 5 each time. This is what we call an arithmetic sequence. So if I'm adding 5, you can kind of see that I could rewrite 8, this one here. Let's do this again. We could write the second term as the first term, 3 plus a 5. And we could write the third term as the first term, 3 plus 2 5s, right? Oh, I see. So this is 1 5, okay? So we could write the fourth term as the first term, which is 3 plus 3 5s. And so now it seems like I'm kind of honing in on a rule. It looks like there's 0 5s being added here. There's 1 5 being added here, 2 5s, 3 5s. And the only thing that's really changing in this sequence is how many 5s we're adding to the original term 3. And I see that the difference here between the number of 5s being added and the subscript is that this one's always 1 less, right, than that one. So what it seems like is that we now have a general formula for this sequence. We could call it 3 plus 5 times n minus 1. And of course, a quick check would be, well, let's see what the fifth term of the sequence, s sub 5, is going to be 3 plus 5 times 5 minus 1. So that's 3 plus 5 times 4, so 5 times 4 is 20, so we end up with 23. And that seems to be right because 23 is 5 more than 18. I also noticed that the 3's are alternating with the 8's, so I expect a 3 in the 1's place at least. So seems like we've found the general term for the sequence. Okay, let's take a look at one more of these. This is example 3, I guess, and we have s sub 1 equal to 1/3. S sub 2 is equal to 2/5. S sub 3 is equal to 3/7. S sub 4 is equal to 4/9, and S sub 5 is equal to 5/11. And what we're after is what is S sub n, the general term. Well, the first thing I notice right away is that the numerator of the fraction is always equal to the term number. So we definitely have something in the form n over something else, right? But the denominator is sort of the important piece, the piece that is a little bit harder to define. So I'll just sort of do some work here on the denominator, 3, 5, 7, 9, and 11. And it appears it's similar to the last one. It's increasing by 2 each time. So I could write 5 as 3 plus 2 times 1. I could write 7 as 3 plus 2 times 2. I could write 9 as 3 plus 2 times 3. And I could write 11 as 3 plus 2 times 4. So I hope you can see that, right? Each one of these is a plus 2. So that means I could write the original one as 3 plus 2 times 0, right? But I got to be careful again here. The number on, I guess, the number of 2's being added is always 1 less than the index here, right? So what I would have to write it as is 3 plus 2 times n minus 1 on the bottom. And I guess the quick check would be to see if this actually calculates S6. I left room here to calculate S6. I think I can just do it recursively just looking at the previous one. So 5 plus 1 is 6, and 11 plus 2 is 13. We would expect 6/13 to come out of this formula if we put 6 into it. Let's see if we do. So S sub 6 is going to be 6 on top over 3 plus 2 times 6 minus 1. So that's a 6 on top, and it's 3 plus 2 times 5, and that gives us 6/13. So indeed, it does check. It seems like we found the recursive formula. So, this is sort of our basic introduction to what sequence work is like. Oftentimes you're given a numeric sequence, and what we're trying to do is generalize it. The way that we generalize is we try to find an expression for S sub n, where n is the nth term in the sequence. I guess S sub n is the nth term in the sequence. It's the index, I guess, on the nth term in the sequence. It's a position. And the way that we often do it is we try to sort of look for patterns in the sequence, or rewrite the sequence in terms of jumps, and try to figure out how many jumps there are and relate those jumps to the indexes attached. So hope that gives you a good start. So we've defined sequences, and we've worked with 3 of them. But it's important that you know that there are different ways that we can represent sequences. So we've already seen that sequences can be given numerically. So these are just lists of numbers, usually with an ellipsis at the end, because of course they go on forever. But you can also represent them graphically. I'll show you how to do that in a minute. And then algebraically, we can represent them using an explicit formula. So what we found in those first 3 examples was an explicit formula. But there's also a way that you can represent them using what's called a recursive formula, and we'll take a look at that here in a second. So let's do this by example. Let's start with this one. So we're going to start with example 1. It's 7 halves, 7 fifths, 7 eighths, 7 elevenths, and 1 half. I'll go ahead and switch over to my ElmoCam now that I have it copied over. Okay, we're supposed to represent this one algebraically and graphically. Okay, so let's go after the algebraic first. S sub 1 is 7 halves. S sub 2 is 7 fifths. S sub 3 is 7 eighths. S sub 4 is 7 elevenths. And S sub 5 is 1 half, which I think you can tell by now that I think what I want to do is leave a 7 on top and call it 7 fourteenths. If what I'm trying to do is generalize this with an explicit formula, then the more things that don't change, the better. So it looks like what we're getting is well, let's just talk about it. S sub n. I can see right away that the top is always 7. And the bottom seems to be increasing by a constant factor, 2 to 5 to 8 to 11 to 14. And that factor is plus 3. I guess it's a constant difference, really. So these are all increasing by 3, which means that 5 can be written as 2 plus 3 once. 8 can be written as 2 plus 3 twice, right? 1, 2. 11 can be written as 2 plus 3 3 times. And 14 can be written as, 2 plus 3 4 times. So that means 2 can be written as 2 plus 3 0 times. And I think we've gotten our answer here. If 4 and 5 are related by a difference of 1, it looks like it's 2 plus 3 times n minus 1. So 2 plus 3 times n minus 1. So we've got an algebraic explicit definition here. Sometimes people clean these up. You might have to check answers on homework. So we could call this 7 over 2 plus 3n minus 3, which is the same thing as 7 over 3n minus 1, right? And let's just check what S sub 6 is. It's going to be 7 over 3 times 6 minus 1. That'll be 7 over 18 minus 1, or 17. And yeah, that seems to be working right, because 17 is 3 more than 14. 7's in the right place. So I'm happy about that. Okay, so let's take a look at how we could represent this graphically. Of course, you could do this by hand, but I think the easier way to do it is just to hop on Desmos and take a look at this sequence. I think I have it already ready for us to go. I'll put a link to the sequence plotter if you want to use this to get pictures of sequences. The way it works is that you have to input a function first here, and I think I already have the function inputted, 7 over 3n minus 1. I did have to use it for x for the function, but anyway, and then what I have down here is a list of elements. These are position numbers, so right now positions are at 0. And you can generate up to 50 elements in that position number list, and what it will do is plot position and the sequence, I guess, term. So this is what our sequence looks like that we just I guess calculated the general term for. You know, you can use the scroll wheel, of course, to zoom in or zoom out on the sequence. You can also sort of get you know, find out which each, you know, the second number is 1.4, the third number is 3.08, and so on and so forth. And I can tell you that the 30th number in that sequence is 0.079. Of course, it doesn't tell us as a particular fraction, but that's the idea. It looks like, you know, this particular sequence seems to be doing what we call converging. It's getting really close to a value, but never really quite getting there. But we could get as close as we want to that value, right? If I just continue my list out. So for example, if I want to get really, I think it's converging to 0, you know, but I'm not really sure because I'm still above 0. I can increase the number of steps I have to 100, and then just keep going and investigate what's happening as we get closer and closer to the 100th sequence, term in the sequence, I should say. When we're out there at that 100th term of the sequence, we're now down to 23 thousandths, and it appears that it is converging to 0. I hope that gives you a sense of one way to graphically think about sequences. They're really similar to functions. The only difference here is that we're plotting points because these are discrete values. It's not a continuous phenomenon. It's a discrete or, you know, point by point phenomenon. So that's one way that you can certainly think about functions and plot them. There's another way that you can plot functions that the book goes into that you can take a look at, where we just simply place the value of each term on a number line and label them. I'm not as big a fan of that representation, so you'll see me use this one. I feel like this is more intuitive because we're used to dealing with functions in I guess a functional sense. So this is just points instead of lines. And of course, by the way, if you want to see the line governing this, of course, there's the function itself. I have it turned off so that we actually concentrate on the points. Okay, so I hope that makes sense. Let's go ahead and put that away and go back to the slides. So we represented that sequence both by a recursive function, there it is. Sorry, not a recursive, but an explicit function, there it is right there, as well as a graph. Let's see, where is my, there it is. Well, let's take another example here. Here I've been giving a sequence, and it's been defined for me recursively, and I think this is the easiest way to introduce this. It says represent the following sequence numerically and graphically. So what do we have? We have S sub n is equal to 2 S sub n minus 1 minus 3 for n greater than 1 and S1 equal to 1. All right, so I have it copied down. There it is. So this one is an example of a I guess a function that's been defined recursively, and your text goes into this a little bit, and there's a few examples there. But what does it mean to be defined recursively? It's just defining the next number in the function based off of the previous number in the function. So what we know right away from the definition is s1 is equal to 1. And then the n's are greater than 1. So, of course, this is just 1, 2, 3, 4, 5. They're integers, or I should say whole numbers. But if I want to find s2, then what do? I take 2 times s1 minus 3. And that's the same thing as, let's see, 2 times 1 minus 3. That's a negative 1. So that's the way a function is defined recursively. We get the next number from the previous number. So s3 is going to be 2 times s2 minus 3. It's going to be 2 times negative 1 minus 3. And what do we get there? We get negative 5. S4 is going to be 2 times S3 minus 3. So it'll be 2 times a negative 5 minus 3. It'll be negative 13. Let's just do one more. S5 equals 2 times S4 minus 3, which is going to be equal to 2 times negative 13 minus 3. And that's going to be, let's see, negative 26, 27, 20, 29, negative 29. Okay, so here would be an example of a recursive function at play, and this idea of building, I guess, each individual number from the previous number. And that's all a recursive formula really does. How could we represent it graphically? So it seems like if I was forced to, I guess, represent this thing graphically, what I would need to do is I would need to be able to plot from 1 to 5, from the value of 1 down to negative 29. So it looks like if I was to sort of graph this, I would probably write my x and y axes like this. I need a lot of negative y, right? Here's x, here's y. Let's see, so I'll do sort of 1, 2, 3, 4, 5. So if I'm at the first value of n right here, let's say this is 1, I'm up at a value of 1. Let's see, I need to put some scales on the axis. Let's do this as, I don't know, I need to go up to 30, so how about I do 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Let's see, that would be negative 10. This would be negative 20. 2, 3, 4, 5. This would be negative 30. At 1, I'm at 1, right? So each one of these is 2, so I would type 1 right there. I would, plot 1 right there. At 2, I'm at negative 1. At 3, I'm at negative 5. So 2, 4, 5. At 4, I'm at negative 13. So let's see, then I would be down 10, 12, 13. And at 5, I'm at negative 29. So I'd be way down here at negative 29. So it appears like this particular function is not converging. In fact, it seems to be blowing up, I guess, in a negative sense, going to negative infinity. And you can kind of feel that, right? Each time what we're going to do is we're going to take some negative number and we're going to multiply it by 2 and subtract a small amount from that, 3, right? So it feels like what's going on here is something, I guess, a little different than the linear examples that we've seen in the past. Let's see. So let's try to play the game one more way. What if I give you a list of numbers that are fairly, I guess, familiar, but I ask you to represent the sequence graphically and with recursive algebra. So let's take a look at that one. I don't think I need to write it down. I can remember that one. So I've been given a numerical definition. It's just 1, 4, 9, 16, 25. So what do I know? I want s sub 1 to be equal to 1, s sub 2 be equal to 4, s sub 3 be equal to 9, s sub 4 be equal to 16, s sub 5 be equal to 25. In fact, we know that s sub n is equal to n squared, but we've been asked to provide the recursive formula, right? And so that's kind of a little bit harder because we have to look at sort of what's happening from term to term. So this is a plus 3, that's a plus 5, this is a plus 7, and that's a plus 9. So it appears that what's happening is we're adding a little bit more each time, right, to the term. So one way we could kind of think of it is, you know, to get from term 1 to term 2, I add 3. And then to get from term 2 to term 3, I add 3 plus 2 more, right? And here I add 3 plus 2 2's. And here I add 3 plus 3 2's, right? So it looks like what's happening here is I'm adding 3 to everything and then some multiple of 2, right? And it gets a little bit interesting. I can see that, you know, it's the only thing now that's changing are these 0, 1, 2, and 3. The 3 plus 2 is constant. So it appears that if I want to know what the next term in the sequence is, I have to add 3 plus some multiple of 2. So that means to get from s, to get to Sn plus 1, actually the way the book usually does it is to Sn, but you can do it either way. To get to Sn, what I need to do is I need to take S of n minus 1 and add to it 3 plus 2 times something, right? And in this case, you can see that the number is always, I guess, 1 less than the term number. Is that right? Let's see. To get from here to here, I am adding, yes, 0, 1 less than n. Here I'm adding 1, which is 1 less than the term number. So this n right here, I'm adding 1 less of it. Let's see if that works. So it appears like it works this way. Let's just check it because we know what S6 should be, right? S6 should be 36. Does this work? S6 is going to be equal to S5 plus 3 plus 2 times 6 minus 1. Let's see if that's true. S5 we're given as 25 plus 3 plus 2 times 5. So it turns out to be 25 plus 13, which is 38. Did I get something wrong? I definitely did something wrong, right? I'm too big. So in other words, I must have added too many 2's here, or I guess 1 too many 2's here. So let's try it again and see. So this is scrapped. Let's try it again and see if S sub n equal to S sub n minus 1 plus 3 plus 2 times n minus 2. Because I added 1 too many. Oh, I can see it now. Yeah, right. Because to get to the S sub 2 term, we're adding 0 2's, and that's 2 less. To get to the S3 term, we're adding 1 2. I see my mistake now. So it appears like this should work. Let's just make sure it does. S6 is equal to S5 plus 3 plus 2 times n minus 2. So we get 25 plus 3 plus 2 times 4. Remember that's 6 minus 2, or 4. So we get 8 plus 3 is 11, and I think that works for 36. Now I'm happy. So this would be an acceptable recursive definition for our rule. Another way we could do is we could clean it up. We could call it S sub n plus 1 equals S sub n, or sorry, I keep calling n plus 1. S sub n minus 1 plus, let's see, it'll be 3 minus 4, so it'll be 2n, if there's minus 1. So I think that would be also an acceptable recursive definition, since these two expressions are equal by the laws of algebra. As far as looking at a graph of this, I think it's pretty easy to imagine what that looks like, but let's draw it really quick. This is just plots of, let's see, so we need to go up to about 25, so I'll do 1 2 3 4, I'll call that 10, 2 3 4, I'll call that 20, 2 4 6, that should do me. I'll call this 1, this 2, this 3, and this 4, and this 5. At 1 we're at 1, at 2 we're at 4, at 3 we're at 9, at 4 we're at 16, and at 5 we're at 25. About there. And so definitely looks like this particular function is blowing up. It's what we expect from a parabola, which is sort of the way that we gained our intuition, is thinking about this as n squared. But here would be your graphical depiction. Remember, no line. This isn't a continuous function. We're talking about just points, right? Sequence. It turns out that we can talk about sequences from the standpoint of whether they converge or not. Convergence is just what you would think about it. We think of it as a limit, and the limit of a sequence is defined in much the same way as the limit of a function. We just say that a sequence has a limit L, and we write that as the limit as n goes to infinity of S sub n equals L. So remember, that's just giving you the value of S sub n, right, at a large value of n, as large as we want. But we say it has a limit. We write it this way if, and here's the big qualifier, if S sub n is as close to L as we please whenever n is sufficiently large. So probably the best way to think about this is graphically. If we go back to our sequence plotter, right now, when you look at the first 5 terms in this sequence, it's not at all clear, to me anyways, that it's converging. But as I bring the number of terms up, it does appear that this thing is getting close to a certain value. It's getting close to 0. Right now, it's 62 thousandths away from 0, and my belief is that it converges. And if I want to get it closer, here it is within 4 100ths. But I can make it as close as I want to the value, even though it doesn't ever actually get there, right? So that's the definition. The definition says that I can make S sub n, the nth term, as close to L as we please whenever n is sufficiently large. So translated into this particular one, I can make the nth term as close to 0 as you like, provided that I can pump up, right, the number of points that I plot. So that's the general definition for convergence with sequences. It's really similar to what we see with functions or limits. So we say that if a sequence limit exists, it converges. If it doesn't, if no limit exists, we say that the sequence diverges, or usually it goes to infinity or doesn't converge. There are examples where sequences don't converge, but also don't go to infinity. Just consider the sequence 1, -1, 1, -1 continued on. That one diverges, but is obviously not going to infinity. There's two important rules to remember from previous study if we want to think about the convergence of sequences, and here they are. Rule number one is that the sequence S sub n equal to x raised to the n converges to 0 so long as the x is less than 1, and actually the absolute value of x is less than 1. That means that x falls in the interval -1, 1, right? So as long as we have a fraction there, and it can be a negative fraction, right, that sequence will converge. Let's just take a quick look at one of those and make sure that we understand that. So let's take this as 1, what is it, x, let's take 1/2 and raise it to, I want to go outside to n. Let's take this back a little ways. So here's a picture of the first, I guess, 11 terms in the sequence, and sure looks like that thing is getting close to 0. In fact, it gets really close to 0 quickly. It's kind of fun to play around with, well, what if I had something that was closer, so let's say if it was like 5/6. So I can see now that the convergence is happening a little slower, compared to 1/2, and I guess that should make sense to you. You're basically at each term you're taking 5/6 of the previous term, by adding another multiple of 5/6 in there. So this thing is being cut down a little slower than 1/2. In fact, you can get, you can play this game kind of, you can make things really close to 1, like let's say 499 over 500. And then things like, look, whoa, it doesn't seem like it's converging at all up there. But if I let things go out a little bit further, things start to seem like they're dropping. If I run it out to 1,000, and suddenly it starts to look like it might be getting close to 0, or closer to 0. The 1,000th term by that point is well, it's about 135 thousandths. But I guess the idea is that this will converge eventually, as long as this number is less than 1, strictly less than 1. What about if the number was equal to 1? What do we get there? If I had just the number, I don't know, 500 up here, then it should make sense to you that this is just the constant function 1, right? All it's doing is giving you a list that's all 1s. Okay, what about if it's negative? So let's take something like negative, I don't know, 1/3. Let's make this back down to, pull this back down to 100 and zoom in, because this is where things get kind of interesting. And actually, I'm going to make it -2/3 just to make it converge a little slower. So then we get this picture. Maybe we'll change this back to 100 so we don't have quite so many points on board. And you see the first term is -2/3, and the second term is -2/3 squared. So that's going to bop it up to positive, and then negative, and then positive, and then negative. But again, you can see that even though I'm bouncing up and down around, bouncing up and down across the x-axis, that eventually what happens is I get pretty darn close to 0. And in fact, challenges Desmos's accuracy once I'm past, let's see, the 18th term. So it seems like at the 18th term we are effectively at 0. So kind of an interesting thing. If we want to see one that's, you know, I guess going to 0 a little slower, what we do is we pick a negative number that's closer to -1. So something like -4/5 maybe. So there's a kind of a neat one. You can see that it's negative, then positive, then negative, then positive. But by the time we get out to a sufficiently large enough term that we've converged close to 0, as close as we'd like. Okay, so definitely a useful rule. We know that anytime we have x to the n where that x is some fraction between -1 and 1, non-inclusive, then we get convergence. Rule 2 is this one. It says that the sequence s sub n 1 over n to the p converges so long as p is greater than 0. So long as the power there on the exponent is greater than 0. So let's go ahead and take a look at that one. So it's 1 over n, which in this case is x, right? Raised to the any number that's greater than 0, right? I don't know. Let's try x raised to the 1. I'll get rid of this n. So sure looks like it's converging to me, and I guess it makes sense to me, right? Is the larger the value of n that I put in here, the smaller, you know, like 1 is 1, the first one's 1/2, second one's 1/2, and this will be a third, and so on and so forth, right? So this one will be a quarter, this one will be a fifth, this one will be a sixth, this one will be a seventh. So what we're doing is we're effectively just scrolling through all the unit fractions: half, third, quarter, fifth, sixth, seventh, eighth, ninth, and so on. So certainly by the time we're out to 1/40th, we're at that number. At 1/50th, you know, we'll have 2 100ths, I believe, because 1/50th is the same as 2 100ths, and so on. So I hope that makes sense in terms of that number. What's kind of interesting though is, you know, and I guess it makes sense to me that if that number is squared, then we're converging even quicker, right? Because the number on the bottom is getting large faster. But it's sort of interesting is that, you know, I can put a number like 1/2 in there, and we still converge. We converge a little bit slower, right? By the time I'm at 50, I'm down to about a tenth. If I go out to 100, I'm down to, I guess, 1/10 exactly. Yeah, that makes sense because I'd have 1 over the square root of 100, and the square root of 100 is a tenth. So you can see that as I go out, I can get this thing to flatten out to 0. If I pick numbers that are really close to 0, like 1/10, then of course the convergence is slower. But eventually this will come down and meet the horizontal axis. If I put numbers down here that are really close to 1, we get the first graph that we saw. So I hope that's a convincing enough, I guess, picture of this rule. 1 over n to the p always converges so long as p is greater than 0. So let's take a look at a few examples and how we might be able to use that. And I'll write the first one down. So this is number 1. I'll go switch over to my ElmoCam. So 0.6 to the n, and the question is, does it converge or diverge? Well, we can see it's in the form x to the n, and here x is equal to 0.6, and since 0.6 is strictly less than 1, we can apply rule 1 here to say that the limit as n goes to infinity of s sub n is equal to 0, right? So this one will go to 0. Should make sense to you. We're just taking 60% and 60% of 60%, 60% of 60%. So if you want to think of it this way, we're taking 60% of 1 for at n times, I guess, to get to the nth term. I hope that makes sense. Let's take a look at a little harder one. Here I have s sub n is equal to 1 minus e to the negative n all over 1 plus e to the negative n. Let's take a look at that one. Well, this one's a little bit harder to see up front. So let's just sort of think about it from a limit standpoint. If we want to take the limit as n goes to infinity of this fraction, 1 minus e to the negative n, 1 minus e to the negative n, oh, but it's plus down below, then, you know, we can use some of what we know about limits. Remember that limit of a quotient is the quotient of the limits, so we can take the limit of the top. Move that shaky bottle. 1 minus e to the negative n all over the limit of the bottom. 1 plus e to the negative n. Okay, so far so good. Now we have a limit of a difference and a limit of a sum. We can take each of those limits. We know the limit as n goes to infinity of 1 is just 1, but this is the piece that's changing. And the limit as n goes to infinity of 1 is just 1, and this is the piece that's just changing. So I'll just apply my limits inside to each of the exponential functions. It'll be 1 minus the limit as n goes to infinity of e to the negative n all over 1 plus the limit as n goes to infinity of e to the negative n. And so now really what happens is we have to know what this limit is doing, right? And this is where it kind of helps to think about, well, what's going on here? So first of all, we can think of e to the negative n. So e to the negative n is the same thing as e to the negative 1, right, raised to the n. And we know that e is roughly 2.718 dot 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 and changes. So this thing is the same thing as 1 over e raised to the n, which is sort of roughly equal to, you know, 1 over 2.718 change raised to the n, right? And now I can see that this thing is a heck of a lot like the previous one, right? It's some fraction between 0 and 1 raised to the n. And so this notion tells us that then that the limit as n goes to infinity of e to the negative n is going to be the same as the limit as n went to infinity. Sorry, I got a little bit off the screen there, I realized. It's going to be really similar to this one. We can apply rule 1. And that's by rule 1. So that means that when I was right here, what I get is 1 minus 0 over 1 plus 0. So the limit as n goes to infinity of this sequence is going to be equal to 1 plus 0 over, sorry, it would be 1 minus 0. There's a minus on top. Over 1 plus a 0, which is just equal to 1. So that's kind of interesting, in kind of a different setting, but apparently this particular function I should say sequence, should settle out at 1. Might be kind of neat to just stop here and take a look at what that looks like as a graph on Desmos. So let's do it. Oops. I want to get rid of everything there. And I'll put the quantity 1 minus e raised to the negative x, that whole thing, divided by 1 plus e raised to the negative x. And I think I have it right. Yep. So again, I'm using x's here, not n's, because this is the way that Desmos likes it written for functions. But I have a list of n numbers where I'm plotting n comma f of n, and now we can definitely see that it seems to be converging, and it converges really quickly to 1. So it seems like by about the 10th term, we're up to the machine accuracy of Desmos, and this particular function is converging to 1. And what was kind of neat is that we had an intuition about that before we went and looked at the graph, just by applying what we knew about convergence. Let's take a look at one more example. Let me write it down. S sub n is equal to n squared plus 1 all over n. So let's see, we could create a few of these, I guess. S1 is going to be 1 squared plus 1 over 1, so it looks like it's 2. S sub 2 is going to be 2 squared plus 1 over 2, so that's 5 over 2. S3 is going to be 3 squared plus 1 over 3, so that's 9, 10 over 3. This is about 2.5, right? This is what, 3 1/3. S4 is going to be 4 squared plus 1 over 4. 16 plus 1 is 17/4, which is 4 1/4. I mean, at least at first glance, it appears that this thing is not converging. But let's take a look and see if we can apply what we know about limits to see what we get. The limit as n goes to infinity of s sub n is going to be the limit as n goes to infinity of n squared plus 1 over n. And one thing I notice is that we get this fraction that we could split up, so we could call it the limit as n goes to infinity of n squared over n is just n, and 1 divided by n is just 1 over n. And this is kind of interesting because, for this one, I would think this piece would be going to 0, right? But this piece, we can easily see that, that when we apply the limit to n and we apply the limit to 1 over n, this one we know from rule 2, this one goes to 0, right? Remember, the exponent on this one is 1, right? And it said anytime we have 1 over n to the p, so long as p is greater than 0 and this p is greater than 0, this thing is going to go to 0 because rule 2 says it will. But looking at this, like, what's the limit on n as n goes to infinity? Well, this thing is definitely going to infinity, right? And just continues to get large. So what's kind of neat to think, though, is that this thing is getting very, very close to the value of whatever n is as n goes to infinity, right? So it's behaving basically like the identity function. You give me an n, I'll give you an n back. But this definitely diverges. I hope that makes sense. So I wanted to give you at least one example where we had divergent function, and this would be one. All right, let's go back and talk a little bit about last few things here. Boundedness and monotonicity. So it turns out that we can think of sequences as being bounded if there are numbers k and m that are above and below any value of the sequence. So any convergent sequence will always be bounded, and bounded sequences, however, are not always convergent. Let me just explain that really quickly. If I move this out of the way and this one out of the way, I should get back to my note. Let's see. So, this would be an example of a convergent sequence we just took a look at, and it's definitely bounded, right? It's bounded by, I don't know, y equals 0 on the bottom, and let's say y equal 1 on the top. And I don't know, you could even say 1.1 to make it look, it's definitely bounded by those two curves. In other words, those two constants. In other words, it's always between 0 and, I think it's actually between 0 and 1, because I don't think it comes above. I think it approaches from below. But since it's between those two, we could say that it's bounded, and we should be able to do this for any convergent sequence. In other words, anything that converges should have sort of an upper and a lower bound that it doesn't go outside of. Yeah, there are examples, though, where bounded sequences are not always convergent. So one example of that would be, let me go to my ElmoChem. How could we get something that's bounded but not convergent? You just need to think of, like, if we had something like this. So we could think of it as S sub n is just the number -1 raised to, let's say, the n plus 1 power. So in the first term I'm squaring, in the second term I'm cubing, and I get a negative, right? And so on. So this particular, is a perfectly good sequence. If we kind of think about it as a graph, we're basically bouncing between -1 and 1. For the first term I'm at 1, 2, 3, 4. Second term I'm at -1. Third term I'm at 1. Fourth term I'm at -1. Fifth term I'll be at 1. And you get the idea. We can definitely say that this thing is bounded because it's always in between 2 and -2. So it's bounded because it bounces in between those two, but it's definitely not convergent. We're just bouncing between two numbers, and we can't get as close as we like to the one value that it converges to by simply taking a large enough index on the sequence. So just a caution, I guess, that if you're convergent, then you're bounded, but if you're bounded, you're not always convergent. There is this kind of neat thing, though, called monotonicity, and it says that a sequence that's either strictly increasing or decreasing we can call monotone. So this would be things like exponential decay or growth, linear decay or growth, certain regions of parabolas that are strictly increasing or decreasing. So these sort of functions, or I guess rules, are called monotone. And what's neat about this is that if a sequence is bounded and monotone, then it has to converge. So if it's trapped between two, I guess upper and lower extremes, and it's moving in one direction or the other always, in other words, if it's either climbing or falling, then it's just got to converge. And I wish we could go into the proof for this. It's actually in the supplement to your book, which is available online. It's a fairly complicated proof, but it should make sense to you intuitively. If you're trapped between an upper and lower bound, you're bounded, but you're constantly increasing. then you have to at some point settle out to some value. So that's kind of a neat way to think about sequences. Let's see if we can apply that idea here. So number one is S sub n is equal to 3 plus e to the negative 4n. And number two, S sub n is equal to negative 1 to the n over n. Okay, so we could go after the limit and see if we could figure that out, but let's see if we can use monotonicity and boundedness to get a sense of what's going on here. So I can see that this number is 3, and I'm adding to it a negative exponential decay, I guess. So S sub 1 is going to be equal to 3 plus e to the negative 4. S sub 2 is going to be equal to 3 plus e to the, let's see, times 2, negative 8. You can kind of think of this as 3 plus 1 over e to the 4th. You can kind of think of this as 3 plus 1 over e to the 8th. Let's do one more, just to 3 plus e to the negative, let's see, 3 times 4 is 12. So this will be 3 plus 1 over e to the 12th. And of course, 1 over e to the 4th, this is like a 2.7 to the 4th, 2.7 to the 8th, 2.7 to the 8th. So, so we have a very big number here, right, in the denominator, and we're taking 1 over a big number. So this is a very small number. So we're adding that to 3, and that's what we'll always do, right? So we could say it's bounded above by a number that it's always strictly less than, right? And since these are smaller numbers being added to 3, this is the biggest number. I don't know, we could say that this is certainly smaller than 4. It's bounded above by y equal 4. And bounded below by y equals 3, right? I mean, we never quite get to 3. We're always adding a little bit, this tiny little piece to 3. So this is definitely bounded. And the other thing we can see is that it's getting smaller, right? We're adding less and less each time. So it's monotonically decreasing. So we can apply what the theorem says, this thing must converge. So again, if it's bounded and it's monotonically moving in one direction or the other, in this case we're decreasing, then you just have to, it just has to converge. There's no way that it can be bounded and be be either increasing or decreasing monotonically and not arrive at a certain value. All right, let's take a look at another one here. Let's take a look at S sub 1. That's going to be, let's just do this carefully, negative 1 to the 1 over 1. So it's negative 1. S sub 2 is going to be, let's see, negative 1 to the 2 over 2. So negative 1 squared is going to be 1. So this is 1/2. S sub 3 is going to be, let's see, negative 1 to the 3 over, let's see, 3. So this will be negative 1/3. And S sub 4, it appears that what this does, it just alternates positive, negative, and the denominator, of course, is just the, so this is going to be a positive 1/4, the index on the term. So it looks like what this thing is doing is it's bouncing between, I mean, let's just take make a little picture of this, right? 1, 2, 3, 4. Here'd be 1, and here'd be negative 1. So at 1, I'm at -1. At 2, I'm at a half. At 3, I'm at -1/3. Let's say about right there. At 4, I'm at a quarter. So you can kind of see it's going like this, to that, to this. And of course, we're going to be at a fifth at 5. So even shorter. So it does appear like this thing is converging, but we cannot use this particular theorem that we just stated. And the reason we can't is because this thing is not monotonically increasing or decreasing. So we're inconclusive on this one, at least in terms of using the theorem. We're going to have to dig into it with limits and try to get a sense of whether it converges using a limit. And, you know, that's going to be a little bit harder to do. But I think you can kind of see what's happening here, right? This denominator is going to infinity, and we're getting either +1 or -1 over infinity. And you know, that's going very close to 0, either from above or from below, but certainly not approaching monotonically from either above or below strictly. Okay, well, I hope that gives you a good sense of what's going on there. That's really all I think I had for you in terms of lecture for this chapter. I will post my handwritten notes here next to the video, and I'll also post a link to the Desmos sequence plotter that I used. And I wish you luck in your homework, and I'll see you upon my return.